Good afternoon, everybody. Welcome back to lecture number 18. It's recording, right? So today we will continue our discussion for the electric machines, induction machine, and here is the slide that I skipped where the phasor moves at time 1, 2, and 3. Here's the F, here's the F, here's the F. I explained it to you. Maybe these are one of the conceptual questions in the test, okay? Last lecture, what did we discover? We discovered in the previous example a very interesting idea. What was the idea? How much external resistance per phase should be connected in the rotor circuit so that the maximum torque occurs at start. So we made the maximum torque, instead of it at slip max, we shifted all the way to slip 1, making it class D or C. Okay? This is the first idea of motor control. So the idea here was to equate the equation of S max, which has R2 squared, so this is S max equal to square root of 2. The original equation is, you square both of them, and then you will have R2 added plus R2 prime equal to R1 prime plus X equivalent squared. So the R1 squared plus X equivalent squared, square both sides, and subtract. No, this is a number. You can calculate this number. Minus the 0.2, you should get 0.831. So if you add 0.831 to the wound rotor after the slip rings, you should be transferring the torque to be at the start. So the maximum torque will be here at the beginning. Okay? Now, today we will discuss modes of operation. There are 3 modes of operation for induction machine. The first mode of operation is the regular one, the motoring mode, from slip 1 to 0, or from speed 0 to synchronous speed. This is the typical motoring curve. So the speed is between 0 and S, and the step is between 1 and 0. And this is most of the 360 problems were there. The second mode of operation is the generating mode. The moment you're applying mechanical force such that the speed of the rotor is faster than the RMF, the rotating magnetic field, then what will happen is we are in the generating mode. And this is the wind farms, they're operating at this mode. And it is also important for what we call regenerative braking. Is basically, sometimes if you go downhill in the car, you're driving Tesla is going down. Do you think the speed would be fast on the motor or slow? It will be fast. كانت تحط على الإنه وتحضر السيارة. If you don't apply any force, any speed control, because when you hit the pedal, like when you hit the pedal for EVs, you're controlling the signal. You have a control. You're actually having a control in your machine. But if you leave it free spinning, it will increase the speed of the rotor shaft above the synchronous speed, and now you will be generating electricity. So EVs during this operating mode, what they have is they capture that energy and store it in the batteries. But the most interesting form is the plugging form, which is the sudden braking form. This is very important, Ahmed. This is very important. What is happening is, what is that in the sheet? What is happening here is, let's say I'm driving my car and I'm at very low speeds. How can I make the speed sudden? How can I make the brake sudden? If, for example, you're driving, there is a car in front of you and you want to hit the brake. So electric vehicles use a very smart technique. What do you notice about the speed from 0 to minus ns? It is same as this speed, but it's negative. So if the rotor is rotating counterclockwise, it has to be rotated clockwise, and vice versa. But can this be mechanically feasible? Can you hit a command, the car is driving 100 miles per hour, and you tell it, oh, shift your direction of rotation? That's not a good idea. This is very similar if you're driving a car and you put it in the R. If you drive a manual car or an automatic car and you suddenly put it in the R, what will happen? You'll get an error. So this is very similar. It's like reverse mode. So what is happening is we call what we have the phase sequence changing. Phase sequence change is you have your induction machine, you have A, B, C. For some reason, here is your shaft rotating clockwise. You keep the shaft direction rotating this way, but you only change C with B. What will happen if you change the electric supply of the motor? The RMF would rotate the other direction. So this way it will force down, it will go into the plugging mode even though the direction of the speed is the same, because it's opposite of the direction of the flux. Get it? We will explain this later. So in the plugging, if you want sudden braking, the best way is just to change the phase sequence. And this might be a question in the test, okay? So let's explore what we just discussed. The motoring mode, if the stator terminals are connected to three-phase supplies, this is the rotor will rotate in the direction of the stator RMF. If you flip the direction of RMF, then the speed will be the opposite. This is the natural motoring mode of IM, steady state speed N is less than the synchronous. The generating mode, the induction machine can be adjusted so that the speed of the system is higher by external factor than the synchronous speed, and the system rotates in the same direction. Still we are in the same direction. This is one of my favorite questions I'm going to have in the test. So I didn't write the test, but I will say, for the generating mode, we are in the same opposite quadrant or none of the above direction of the RMF. So memorize, okay? حفظ, okay? حفظ, please. Okay, that's the only way. Or I'll give you hard problems. Which one do you want? حفظ, خلاص. The induction machine will produce a generating torque. We will have a torque. This torque that is acting opposite to the rotation of the rotor, okay? Or acting opposite to the RMF. So always motoring, generating, speed is in the same direction of the RMF. However, the torque produced in the generating mode is negative. In the motoring mode, the torque is positive. What does positive mean? Positive means is in the direction of the RMF. Negative in the generating is in the opposite direction. حفظ. Again, the generating mode of operation is utilized in the application we call it regenerative braking. It's braking, but it regenerates electricity. And this is the basic concept of hybrid EVs. The hybrid vehicles, they utilize the regenerative braking to maintain their small batteries. The batteries in the hybrid EVs are not as big as in the pure EVs. Plugging mode is utilized where the drive system is required to drop suddenly. Again, this is a very spot where I can ask you a question. Plugging, if you want to have sudden drop, you use plugging mode, motoring mode, regenerative braking, generating mode. It's trick. صح ولا لا? Is it trick? Yes. So only those who memorize the slides will say it's plugging mode. Those who did not memorize the slides will say regenerative braking. Clear? Okay. So we agreed on this question. Suppose that the induction machine is running at steady state speed. If the terminal phase sequence, instead of ABC, you have an ACB, you just flip the wires. And you don't flip the wires. In real life, the inverter will change. if you remember the inverters, who took the power electronics? You remember the inverters, the MOSFETs, you send firing signals. So you just change that sequence of the firing signals, and then you connect C before to that cable instead of B. So you do the phase sequence by means of power electronics. You don't do it by physical wiring, because you cannot change the wires if you're driving the car. That's not logical. So you change it by means of power electronics.
What about the switches, doctor? Contactors?
Yeah, the contactors are the same. Your pulses are different. And instead of sending pulse to 1 and 2, you send it maybe to 1 and 5. There are 6, the H bridge. Get it? We're not going to go into the details. This is Dr. Mahmoud Qassas' course. Here we're just using his ideas to explain the concept that we have, which is the phase sequence. The phase sequence would make the RMF rotating in an opposite direction, making the speed rotating, making the slip negative. The motor will come to 0 speed rapidly and will accelerate in the opposite direction unless the supply is disconnected at 0 speed. So this is a type of control for plugging mode. So let's go to speed control of 3-phase induction machine. Any question about these? Clear? So here what do you notice? Here when we added the external resistance, we changed the maximum torque slip. We started now at a very high torque because now we have elevator, for example. The concept that we talked today, it's rough. Please focus. It's a tough lecture. That's why I couldn't make it online. Using the approximated equivalent circuit. So we're using circuit 2. If you took 360 with me, but this is the only thing is we move the branch from here to here. Why? To make the current I magnetization plus I2 prime connecting all the resistances in series, R1 and R2 prime over S. So this is the closed term, the closed form expression. It is a 3V1. It is line to line or phase? Nawaf?
Phase.
It's phased. R2 prime over the summation of 2 resistors squared plus X equivalent squared times the slip times synchronous speed. Now let's do approximation. Let's pretend X equivalent squared is much smaller than the summation of 2 resistors. So this term is gone. Also let's make another approximation. R2 prime over S is much larger than R1. So this term is gone. So you will have 3V1 square R2 prime over R2 prime square over slip times omega S. If you do the algebra, you will end up with this nicer expression. So this expression is the one we are going to use for speed control. Who's doing the formula sheet? Not here today? Tell the formula sheet guy to put this equation. This is very important for the test. Any question about this equation? So what do we notice? If you increase the volt higher, your torque will be higher. If you increase the resistance, your torque will go down. If you change the speed, the slip, meaning if you make the slip larger, means if you make the speed lower, isn't it? If you make the slip lower, the speed slower from motoring mode, making the slip larger, your torque will be larger. Okay? Omega S is from the supply frequency. Probably we will talk about it later. But if you decrease the frequency, what will happen? 50 hertz will have a higher torque than 60 hertz, because omega S is smaller for 50 hertz. So what are the types? This one, memorize this figure. You have to memorize it. Okay? There is 2 types of induction motor control. Either stator side or rotor side. In the rotor side, we already explored adding resistance to the rotor. What is the other type? The other type, we'll talk about it later, it's called the slip energy recovery control scheme. So So you have to memorize slip energy recovery control scheme. The stator side control, there is 4 types of controls. We either control the voltage, because the voltage is connected to the stator, or number of poles. How do we change number of poles? By changing the windings. It's not a permanent, there is no permanent magnet induction motor. Okay, I'm going to ask a question in the test. An engineer claimed that he or she is manufacturing a permanent magnet induction motor. Is this a good engineer or bad engineer? Bad engineer. That doesn't make sense. Okay? So changing poles means changing of the windings. If you change the windings of the stator, you can change number of poles. And if you notice that the 4-pole machine would have 4 clusters of windings across the stator. Or frequency, or voltage over frequency. Basically, you change the voltage and the frequency together as a ratio. Okay? The best one, of course, is the one that sounds more technical. So which one of these sounds more technical? Slip energy recovery and V over F. If it doesn't sound technically challenging, then that's not a good control. Okay? Clear? So in these 6 boxes, you pick 2. Which one are the best? Slip energy recovery, V over F. Okay? This is the tough table. Now, this tough table, again, in the negotiation phase, 72 hours before the test, maybe I will allow it, maybe I will reject it, but either way, you have to understand. Either way, you have to understand. So, do you remember this equation? This is the simplified torque equation. You agree with me?
Yes.
So the simplified torque equation, this is only at small slips, from no load to full load region. This equation is better only at small slips. Reactances and R1, X equivalent, and R1 are neglected compared to R2 prime over S. Therefore, comparing 2 points, this is not clear, but I will write it down. I'll fix the slides. So this equation is nothing but T1 over T2 equal V1 squared S1 P1 F2 over F2 squared slip 2 P2 F1 R2 prime plus R at over R2 prime. So we're taking ratios of 2 different points of torque, 2 random points. If you plug these equations, you put V1 or S1 or R2, the torque at 1 has these parameters, F1 prime, S1, P1 over F1 over R2 prime. The second torque has F2, S2, P2, F2, and R2 prime plus R add, or external. So we're comparing these ratios. We're comparing them at column 1, column 2, column 3. What does it say in column 1? Constant torque, linear with speed torque, quadratic relationship with the speed. There is 3 types of loads. The first type of load, it's called the constant torque over the speeds. So here we have the torque, here we have omega or n, speed. The first one is the constant torque. Torque is constant no matter how you change the speed. Regardless whether this is maybe for one common application is a flat road. If you increase the speed or if you decrease the speed, the torque is constant. The other relation of the torque is the linear torque. Maybe usually it doesn't need to start from 0. It maybe start from here. So this is T proportional to omega. The last type is the fans, which usually the quadratic relationship, and it's usually like that. So here torque is proportional to omega squared. There is a 3 different types of load. For every motor, if let's say, if this is the maximum torque, look at the intersection. So the green curve is for the motor. The 2 red and the black curve is for the load. So this is load. This is TL is constant. The intersection here and the intersection here and the intersection here is your point of operation. بمعنى the intersection between your motor torque speed characteristics and your actual load, that intersection, this is your point of operation. It means under this load, the motor will behave that way. Under this load, the motor will behave, will cross at 2 different points, either high speed or low speed. Under this load, this is the, okay, no, that's wrong. Yeah, this is the intersection. So we have also here another intersection. Depending on your speed, you're only allowed to have the no, that's not a point. هذه load. This is not. هذا الأسود. This is the red. This is the red. So this is point 1. This is point 2. This is point 3. What do you notice about your points of operation? They're sliding in the linear mode. So if you have a constant torque, you will have the load constant, so your shaft will adjust at this slip. For linear, at the slip. For quadrature relationship or fan, we call this fan. Okay, we call this fan load. Okay? Fan load. So the relationship is this way. If you divide torque 1 over torque 2 for a constant, what's the result? 1. If you divide torque 1 over torque 2 between two different linear loads, the change will be a function. So what we propose here is you should have 1 minus S1 times F1 times P2 over 1 minus S2 times F2 times P1. Because why? You remember omega is 2 pi over, what's the relation to pi over 60? N. If I have omega 1, and what is N? Here it's time to use my notes. Do you remember that omega is 2 pi over 60? What is N?
120.
120 F
over
P. So to change, to have omega 2, so this is F1 P1. To have omega 2, another speed, then you should have 2 pi over 60 in 2 over 2 pi, which is 2 pi over 60, 120 F2 over P2. Do you agree with me?
Yes.
However, this equation, no, my bad. This equation is only for synchronous speed, so you need to add 1 minus S. 1. Here, 1 minus S to Y, because this equation is only for synchronous speed. So now we add 1 minus S. Do you remember N equal N S times 1 minus S? So now we add these terms. Divide these omega 1 over omega 2, you should get this relationship. Clear? For square, you just square everything. Clear? So now, do you understand the first 2 rows of this table? The first row is the type of the load. Is it constant or linear or quadratic? Relationship with the speed. The second relationship is if you take torque 1 over torque 2, basically a constant speed over constant speed, or torque 1 over torque 2, which is speed 1 over speed 2. If you do speed 1 over speed 2, use this board to derive these two numerator and denominator. If you use a speed square, what will happen? 1 minus S1 F1 P2 square. If these two square, the denominator here square. Clear? Now, control technique. How many control techniques we have? This is 5. Some of them from the only ones that are missing is V over F and energy recovery. We're putting everything here. Okay? Here what is happening? Go to this equation and change V1 and V2 and slip 1 and slip 2 and remove everything else. So if you go to this equation, you have V1 over V2, keep P1, P2, F2, F1, the resistance, get rid of them. Put it in the left hand side. Would equal to this ratio, 1. For the resistances, remove the voltage, remove the poles, remove the frequency, keep the slips and the resistances. Keep the slips and the resistances, make it equal to 1. For the third, the frequency, remove V1 and V2, remove P1 and P2, keep the frequency, keep the slips, remove the resistances. So you have S1, F2, S2, F1 equal to 1. The last part is P. Keep P1, S1, P2, S2, remove everything else. The last part is V over F, keep V and F. So keep V1 and F1, V2 and F2 with the square, and slip 1 and slip 2, remove the resistance and the poles. You should get this term. Equate them with whatever you have here, 1. With 1 is easy. But for this it gets more complicated. It's tricky. Because the left hand side is the same. Did we change anything in the left hand side?
No.
Okay, good. In the right hand side, if it's not fixed here, remove it there. Clear? So here, is there a voltage here? No. So we remove frequency, we remove P, we just maintain the slips. So we equate these two terms with this. Take, for example, the added resistance. Is there any added resistance here? No. Remove frequency and poles, keep 1 minus S1 over S2, equate it to the same one here. For the third one, frequency. Is there a frequency here? Yeah. So keep F1, F2, 1 minus S1 minus S2, remove the poles, and same for the left hand side. And so on. The last part is with the square, same story. You just have the square implemented. So these terms are the same except on the right hand side. The toughest one is this one, V over F. We have V1, S1, F2. It's the same. We remove the poles, we keep the frequencies. If it's a square, we square it. Now, this is the basic idea of frequency control. This is the basic idea of frequency control. Let's see how these things would work out. The first type of speed control is adding external resistance. We already talked to you about it. So what type of load is this one? I'm going to ask someone. What type of load? Is it fan or linear? The dashed line. It doesn't look linear. It looks like a fan. It's x squared, omega squared. Question. How many external resistances do we have here?
3.
No, 5.
Oh, yes.
We have our external at 0, 1, 2, 3, 4. So we have 5. Starting from 0, this is the normal curve, this is the operating point. So what's your operating point? Here. Change the resistance to R external 1, which is slightly higher. Where is your operating point? Here. What do you notice? Your maximum slip got shifted from slip at speed M4 to slip at speed somewhere here. For external 2. Then we push the curve for 3 and 4, and we're operating always at lower torque. So if you add more resistance, you reduce the speed, but you still satisfy the load. You still satisfy the load. You still satisfy. So is there a problem if we're still satisfying the load? From the load perspective, we don't have a problem. The only problem is if my curves do not cross. So what is the advantages? What are the advantages? We have wide range of speed. We can sweep across all the speeds. We have constant maximum torque. That means constant torque is allowed. Constant maximum torque. So the speed, the peak of every curve is the same unless you exceed the limit, so it will be in the plugging mode. You will still have a peak, but where? In the plugging mode. But your peak is fixed. Okay? What are the bad stuff? There's 3 bad things. And this is definitely will come. List the advantage of speed control, list the disadvantage. Again, you have to memorize it. There is no way. Okay? Limited to wound rotor type. Why it's limited to wound rotor type? Because wound rotor types are the only rotors that you can have external. Squirrel cage is not allowed because squirrel cage are short-circuited and you cannot add resistances to them. Lower efficiency due to copper loss. Yeah, we add more resistors, we have more I square R losses. The last part is the maximum slip increases and efficiency will be decreased. Do you remember from last lecture I told you what's the internal efficiency? It was 1 minus S. Do you remember that? Which was 90% compared above the regular efficiency. Do you remember the internal efficiency? Watch YouTube. Watch previous lecture, we talked about internal efficiency. So if you increase the slip, what will happen? You have less efficient system. So if in your internal efficiency is lower, then your total efficiency will go lower. So this is why external, the more resistance you add, you operate at smaller speed. If you operate at smaller speed, you become less efficient. Here is some power electronics technique. So this is what we call a chopper. So instead of having RX1, RX2, RX3, you have one big resistor and you switch this using power electronics to get an average RMS. If you switch it more, you keep that breaker open. If you keep that breaker open more, you expose the external resistance on the RMS more. If you close it more, you make it more short circuit. So how do you control that using this device, which is the thyristor? Is this a thyristor?
Yes.
It's a thyristor. It's a silicon controlled rectifier. And the goal of this thyristor is to control the whole system is a chopper. You can have a closed loop feedback. This is not required, except you should know the block diagram. Is you take measurement alpha, which is the firing angle, and you compare the currents and you feed back to the tachometer, which has to do with the speed of your machine. So is there speed control resistance is clear? So here is one example. We will do it later. It's a tough example. But the second part of speed control is what? So any question about external resistance? This is using power electronics to, instead of having external, you just close the breaker. If you make it more short circuit across the time, the more you close this chopper, the less effective external resistance. Okay? This one is the same except that you have closed loop. You feed back the speed to the thyristor. The other type of speed control which is required in the test is varying the speed voltage. So do you remember this equation? 3v1 square s over r2 prime over omega s. Do you remember the maximum torque? If you do the simplification, it's 3v1 square over 2 omega external. Do you remember this equation? Do you remember this equation? The maximum slip, if you ignore r1, it is r2 prime over x equivalent. So what is happening here is you still have the fan load, which is omega square, but here I change v1 and v2 and v3. What do you notice? The operating speed will change. So at V1 we're operating here. At V2 we're operating here. At V3 we're operating here. So is there a problem? No, we still maintain the load. But what do you notice? The peak, the maximum torque at V1 is larger than V2, is larger than V3. So I can increase the maximum torque without changing the maximum slip. Clear? The more V1, the less the speed that you're operating at, but it's not as bad as the external resistance. So what should we memorize? Memorize advantage and disadvantage. So when the advantage is the slip at maximum, SM. What is SM? No, slip at maximum torque. Slip means the speed. So speed at maximum torque is almost the same compared to our the external resistance. Losses are reduced with the voltage reduction. So this is good. You can reduce the voltage, you can consume less power. It's excellent method for starting the fans. So they are lined up with the fans. They are very excellent to start with the fans. Why? Because you maintain the peak torque here above the fan. So you, no matter what changes your volt, you're always gonna make your peak larger than the fan. Now don't go to 50% or no. This is a good way to start the fan. And if you think about it, if you want to control the fan speed, you just increase the voltage, then the fan will spin faster. If you want your fan to be smaller, you just reduce the voltage. Should you add external resistance? Is the fan complicated that it has V over F? Or is it complicated to have, what's the other one, energy recovery? Do we need to have energy recovery mode? Clear? So what do we have here? This is excellent way to control the fan. The bad stuff, the maximum torque is reduced if you reduce the voltage. So you have to be careful that you satisfy minimum voltage above the fan load and limited range of speed control. You can't control the speed of the fan much. The fan speed, to make it spinning slower, is very high. The smaller the fan, the harder it is. Now the easiest fans to control the speed are the bigger diameter ones, so you have to increase the diameter. And how to do it? Using the AC controller. Do you remember this from E360? No, because all of you took the old 360. Those who took the new 360, they studied this. But what is this? You already studied this. This is the AC chopper, but this is a thyristor with firing angle. So if you increase the firing angle, so the firing angle basically would say it will conduct, basically you reduce the AC, the effective voltage RMS for your signal. So where is your output signal? These are different control things, but the original AC signal is this one. You have gate 1, gate 2, and you have the voltage output. So here we chopped this part and this part using two thyristors. One for the positive cycle, one for the negative cycle. I'm not going to ask you how these work because this is a power electronics course. But what is the effective RMS value? Is it more or less?
Yes.
It's a chopped. So now, did we decrease V1 to V2? Yeah, so this V1 becomes V2 because V2 is smaller. So you do it using this circuit. However, this circuit is bad. Why it's bad? Because it has, if you increase the firing angle, you reduce the voltage, you reduce the power factor. Whether it's resistive load or inductive load, with the thyristor, if you increase the firing angle, you reduce the power factor. So because the power factor is highly reduced. Again, this is one of the questions that you have to memorize it for the test. You have to memorize. Put these slides in ChatGPT and ask ChatGPT to give you MCQs. Trust me, ChatGPT will give you a question about power factor. The other type is we use the pulse width modulator. Pulse width modulator is more complicated. You have more pulses. You have D1, D2, D2 prime, D1 prime, and you can chop whatever you want. You can chop whatever you want. This is more preferred because you have wider controllability and better system performance, better power factor, etc. So Dr. Abu Bakr Salim, he put this slide, asked us to do research. So this is activity for you. Create. If you do it, you're gonna get bonus. If you don't do it, you're not gonna get bonus. Send me a one-slide summary about PWL. Just explain in bullets how they work. It's either you do it, it's gonna be counted. If you don't do it, it's not gonna be counted. So this is a brainstorming activity. Okay? And then we will do example 4 and example 5 in the help session of the extra lecture, and they are required in the test. This example is difficult or easy? It's difficult. Okay, so I cannot explain it in a few minutes. However, today we cover these concepts. So I would say the major exam.
Until slide
No,
example 5?
until slide 46.
Okay.
We did not cover. We will cover. It's a problem, but we covered the concept. So here in of exam, I think I dropped one slide. It could be the slide after that complements this example. But we will remind us. We will solve these two examples in the help session, and the next lecture we'll try to solve them and finish. So you can see how many slides you have. 46. The other one, how many slides you have? 90. So you have 150 slides for major one. Okay? So study hard in the vacation and happy founding day.